Alright, let's go over the questions for Unit 4 review. And these deal a lot with those Riemann sums that you've had, but also ask some other questions as well. So for this first one, for Part A, we are, so let's see, let me make this smaller so I can see it over here. Alright, so for this first one, for Part A, we are supposed to use a midpoint Riemann sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of f of 6. So I'm actually gonna, I'm gonna graph this real quick just so you can understand what's happening. And as far as I know, Desmos is completely allowed on the exam, so you can do this as well. So you've got 0, 4, 1, let's do this, 1, 2, 3, 6, and then we've got 3.5, 8, 1.7, oops, 5.8, and 7. So you've got this graph here. Let's zoom in, not quite that much. Let's get that just right. So I'll actually take this where we can take a picture of it. Alright, and I'm going to put that into what I've got over here. Let's make that much smaller so we can see the whole thing. Oh, this is hateful. Okay. Alright, so there we've got a graph that we can use. So, midpoint Riemann sum with 3 subintervals. So if we're going from 0 to 6, the 3 subintervals that we have, we're going to split right here at 2. We're also going to split again here at 4, and then again, oh, let me just, hold on, that's ugly. Alright, let me draw better lines here. So, right here at 2, right here at 4, and then again here at 6, that's where we're going to make our rectangles, and we're going to use the midpoint. So that's, we're not finding a midpoint, we're just using the point that's in the middle. So like right here between the point at 0 and at 2, we would use the point in there at the middle at 1. So that would be our rectangle here. And then down here we would have this rectangle, and then up here we would have this rectangle. Now if you need to do this on the exam, you can actually see what's happening so that you know that you need, let me highlight here, this area, and this area. Now if you're really good at these, you can probably do these from the table without having to write that down or have to draw that out, but if you need to, draw it out because it's helpful. So if we have those 3 rectangles, the width of each rectangle is 2. So we're going to say what we're estimating here is the area under the curve from 0 to 30 of f prime of x dx. So the area under the curve is approximately, don't use the equal sign here because it's not exact, 2 times the height of that first bar, which is right here, this is at 1, so that's 3.5 over here. So 2 times 3.5 plus 2 times the height here. This is your f prime of 3 value, which is 0.8. Plus 2 times your f of 5 value, which is 5.8. That's an 8 right there. All right, so when you do that, this equals approximately 20.2. Okay, now the question did not ask us to estimate the area under the curve from 0 to 30. Oh, I'm sorry, I don't know why I put 30. I've been doing the next problem, and I should not have put a 30 there. Losing my mind, sorry. That right there should be a 6. So, this is the area under the curve from 0 to 6. The question asks us to approximate f of 6. So this is a fundamental theorem of calculus problem here. And the fundamental theorem of calculus tells us if I take the integral from 0 to 6, or 0 to 6 of f prime of x dx, when I integrate f prime of x, I will get I'll get f of x. And I'll need to evaluate that from 0 to 6, which would mean that it equals f of 6 minus f of 0. So that would tell us that the area under the curve from 0 to 6 is equal to f of 6 minus f of 0. So, sorry, f of 6 minus f of 0 then would have to be approximately the value we just found with that Riemann sum, so approximately 20.2. Now, we want to find f of 6, so we need something to plug in for f of 0. Typically, those initial conditions are given to you somewhere, and in this problem they are. It says here the function f satisfies f of 0 equals 20. So there's your point right there, f of 0 equals 20. So we know f of 6 minus 20 is approximately 20.2. So if you take that 20 right there and add it to both sides, then f of 6 is approximately 40.2. So that'll give you your answer for part A. To determine whether the actual value of f of 6 could be 60, or could be 70, explain your reasoning. So this is a weird question. It's a little hard to answer, but we are going to use this value right up here. We're told the first derivative satisfies the inequality that 0 is less than or equal to f prime of x, which is less than or equal to 7, which tells me that f prime of x, the very biggest number it could be is 7, so it has to be less than or equal to 7. So that means that the integral from 0 to 6 of f prime of x dx has to be less than or equal to the integral from 0 to 6 of 7 dx, because 7 would be like if we had the highest value the whole time and it was just 7 here. And so if we integrate that, we'll get 7x from 0 to 6, which is just going to be 7 times 6 minus 7 times 0, which is 42. So that tells us that the integral from 0 to 6 of f prime of x dx has to be less than or equal to 42. The biggest it could possibly be is 42. But again, like the last problem, we're not talking about the integral from 0 to 6. We're talking about f of 6. So we know when we integrate this part, f of 6 minus f of 0 is going to be equivalent to the integral from 0 to 6 of f prime of x dx. So this has to be less than or equal to 42. And we were given our f of 0, which we've already used once. That's 20. So f of 6 minus 20 is less than or equal to 42. If you add that 20 over there, f of 6 is less than or equal to 62. Therefore, f of 6 does not equal 70. Okay, so that's what you'll do for that problem. All right, let's go on to part C. Part C asks you to evaluate the integral from 2 to 4 of f double prime of x. This is another fundamental theorem of calculus problem. So we don't know f double prime of x. We can't find an equation for that, but we do know that if we integrate f double prime of x dx, we will get just f prime of x. And we will have to evaluate that from 2 to 4, which means we'll get f prime of 4 minus f prime of 2. And fortunately, both of those values are on our table here. So that would give us 1.7 minus f, sorry, it's not right, the f right there, minus the f prime of 2, which is 2. So we get that the integral from 2 to 4 of f double prime of x dx is going to equal negative 0.3 for that. Okay. And for our last part for this one, here we have a limit, and it looks to me like this is probably going to be a L'Hopital's rule limit. They really like to put L'Hopital's rule limits at the end of these. They look like complicated limits that you couldn't do otherwise. Sometimes they might just be regular limits, but a lot of times it's going to be L'Hopital's rule. And so for L'Hopital's rule, you have to get 0 in the top and the bottom. And remember, we're not allowed to just say equals 0 over 0, because nothing equals 0 over 0. So we have to first say that the limit as x approaches 0 of the numerator, so f of x minus 20e to the x equals 0. And that would be f of 0 minus 20e to the 0. And f of 0, they told us in the beginning of the problem, was 20. And e to the 0 is just 1, so this is 20 minus 20, which equals 0. So the numerator does equal 0 whenever you plug in 0. So if we do the denominator, limit as x approaches 0 of 0.5 f of x minus 10 is going to equal 0.5 times f of 0 minus 10. And f of 0 is 20, so half of 20 minus 10 is also going to give us 0 here. We can say, therefore, L'Hopital's rule applies. Okay? So you have to say all of that first, or you won't get full credit for the problem. Now what we can do is we can take the limit of the derivatives here. So limit as x approaches 0 of the derivative of the numerator would be f prime of x minus 20e to the x over 0.5 f prime of x, and then that 10, the derivative of it is just 0, so that part goes away. So we're going to plug in 0 now. So we've got f prime of 0 minus 20e to the 0 over 0.5 times f prime of 0. Sorry. And the derivative at 0, we go up here, it was 4. So we've got 4 minus 20 over 0.5 times 4. And so that's going to give us negative 16 over 2. And so we will get negative 8 for that limit. So that's what you'll do for the first question. Okay, so let's go to number 2. And number 2 is not wanting to show up for me, so I'm going to have to make it full screen here. All right, number 2 asks us to use the tangent line to approximate the reservoir in time 32. So for a tangent line, you need W of 30. You also need W prime of 30. W prime of 30 you're going to find on the table right here. It's going to be 0.5. And W of 30 is given to us here because it tells us at time t equals 30, the reservoir contains 125 gigaliters of water. So if we're working that out, we would say that W of 30 is 125. That's our point. W prime of 30 equals 0.5. I know some of you like to write as little as possible, but label those there so they know what you're doing. You're going to say y minus 125 equals 0.5 times x minus 30. And so y equals 0.5 times x minus 30 plus 125. So we can estimate that W of 32 is approximately 0.5 times 32 minus 30 plus 125. And so that's going to be 1 plus 125, which is going to give you 126. So approximately 126 for part A. Or, well, this is part A of this question, but it's number 2 is the way they've numbered it. Number 3 says to use a left Riemann sum with 3 subintervals indicated by the data to approximate the area under the curve from 0 to 30 of W prime of t. Use this approximation to estimate the amount of water, Wt, in gigaliters in the reservoir at time t equals 0. Show your computations that lead to the answer. So I'm going to do the same thing I did on the last problem, and I'm going to pull up Desmos here. And so I'm going to get rid of this table and put in a new one. And we'll have 0, 10, 22, and 30, and 0.6, 0.71, and 0.5. So we're going to need to change our scale on this when you're going out on the x-axis to about 35. Also on that y-axis, I'm going to make it a little shorter. Let's just only go up to about 5 there. And so we've got this graph right here. In fact, I'm going to make that go on. I'm going to make that only go up to about 2. And here I'm going to put -2, 1, so I can get a good picture of my graph. Okay, let me take this picture of this graph and go over here. We'll add it. Right. Oh, that's not what I want. I need to insert picture. Alright, and let's shrink that down a little. Alright, so now on these, what you're doing is you're using your left Riemann sum. So that means your corner of your graph is going to be on the left endpoint there. And so that would look like this. Just like so. Now notice all of these rectangles are not the same width. So whenever you're estimating this area underneath the curve, 0 to 30 of W prime of t dt is approximately, that first rectangle has a width of 10, and its height would be this 0.6 right here. The second rectangle, you're going from 10 up to 22, so it has a rectangle of 12, or a width of 12, and then it'll have a height of 0.7. And then the last, you're going from 22 to 30 right here, so you've got a width of 8, and you have a height of 1 for that one. So we were looking at the differences here between how much we increased, and we're always using the left endpoints. We do not use the 0.5 there at all. Okay, and so whenever you do this, you are going to get that is 22.4. However, this question also asks you not to give the change that we have there, but to tell how much water was in the reservoir at t equals 0. So we know that the integral from 0 to 30 of w prime of t dt equals w of 30 minus w of 0, and we know that's approximately 22.4. In this case, we know w of 30 is 125. That was given to us in the problem right here. At time t equals 30, the reservoir contains 125 gigaliters. So we're going to plug in 125 right here. Minus w of 0 is approximately 22.4. So if we subtract that 125, then we will get negative, we'll get negative w of 0 is approximately negative 102.6, and so w of 0 is approximately 102.6 gigaliters. There. So that would be our answer for number 3. Okay. For number 4, it says, explain why there must be at least one time t other than t equals 0, such that w prime of t equals 0.7 gigaliters per day. And so the key right here, if you look at it, just kind of makes sense. You go from 0.6 to 0.7 to 1, and then back to 0.5. So if you're just looking, even if we looked at that graph that I just had up there, if we're looking at that graph, if we see here, if this was connected, you know, well, right here somewhere, it's got to go by 0.7 somehow, because it goes from 1 down to 0.5. Now, we have a theorem for that they're looking for here, and that is the intermediate value theorem. It is important anytime you talk about any theorem that you tell when it applies, and for the intermediate value theorem to apply, the function has to be continuous. Now, this does not tell us that w prime is continuous, but it does say that this function is twice differentiable. So if this function is twice differentiable, that means it has to have a first and second derivative, which means that the first derivative is differentiable, and if the first derivative is differentiable, then it has to be continuous, because for something to be differentiable, it must be continuous first. So we can say, since w of t is twice differentiable, w prime of t is continuous, therefore the intermediate value theorem applies. Since w prime of 0, w prime of 30 equals 0.5, which is less than 0.7, which is less than 1, or we could say 1 is the same as w prime of 22. Actually, let's see. We could say on the interval 22 less than x less than t less than 30, since we have this happen where 0.7 is between 0.5 and 0.1, there must be some x such that some t on 22 less than t less than 30, such that W prime of t equals 0.7. So that is an intermediate value theorem problem there. Basically, when we talked about that at first, it was like somebody saying that they have never in their life weighed 200 pounds, but last week they weighed 197, and this week they weighed 202. At some point on their journey from 197 to 202, they weighed 200 pounds, even though they didn't at the time they were actually taking their weight. So that is our intermediate value theorem. And our last part, number 5, is a related rates problem, and we have a formula. A equals 0.3 W to the 2/3, and it gives the area of the surface of the reservoir, and it's in terms of W of t. We're supposed to find the instantaneous rate of change of A in square kilometers per day with respect to t when t equals 30. So A that's a 5. A equals 0.3 W to the 2/3. So if we take the derivative with respect to t here, we're doing dA dt, and that is going to equal 0.3 times 2/3 W to the negative 1/3 times, we got to take the derivative of W with the respect to t. And so if we're finding dA dt such that t equals 30, then that's going to be 0.3 times 2/3, and then W of 30 is going to be 125, because that was given to us in the original point. That's what we've used for all these other parts. So this is going to be 125 to the negative 1/3 times the derivative at 30. The table here tells us is 0.5. So we could multiply this by 0.5. Now, on AP exam, just leave this alone. You don't have to simplify it all. You will have a calculator just so you can see. I'm going to tell you that this is 0.2 if you simplify it down, and this would be in square kilometers per day. So that would be your answer for this problem.